Okay. So, and what I view this as is the what happened. I view this as kind of creating an ambient healthcare intelligence. That's kind of the goal. And so a person, whether they're at home and whether they're have something wearing something or not, or in the environment at home, or they go out in the city or in any other environment, they bringing all their healthcare information with them, and it's exchanging with the Internet of Things and providing a more general healthcare environment for people. And so for today, I have two main themes. The first is really, I'd like to talk about some of the work we're doing that I believe we're kind of moving towards ambient health intelligence that I show over here. And this includes, wearables and in-situ systems. And these are the kind of underlying technology to build a cognitive assistant. And the cognitive assistant is going to be using machine learning and natural language processing. And the second theme is looking at one of the modalities of sensing is the acoustics. And so when we have cognitive assistants over here, there is a lot of voice we're using, so we can use that to look for mood and use for anxiety and so on. So I will talk about this ambient intelligence on smartwatches to start, and then look at more specifics about mood detection. The first part will be a little bit more high level. The second part, I'll go into more specific solutions. So if we're going to put a cognitive assistance on a smartwatch, what we'd like to do is move towards general healthcare intelligence, not general health intelligence. That's way downstream, I think. But if we can be focused more on your problems and your health, I think we can get closer to a general intelligence. And to do this, we need to kind of combine services. We don't want one-off apps. So every app does its own thing, and you have to load all these different apps and so on. So it'd be better if it was all kind of being integrated. And so when we do this on the smartwatch, though, we will interact with internet healthcare services. We will support conversations. This is especially helpful for elderly who can't see the smartwatch very well or can't hit the right buttons on the smartwatch. The outcomes would be reminders, suggestions, alarms, and these things also, people should be able to ask questions about them, and it should be explainable. You just don't make recommendations without explaining it. And we must focus both on physical and mental health. New things can come up, like the pandemic came up, so we try to expand our services to include various aspects of the pandemic. And of course, then privacy is a really important problem, but we're not going to discuss that today. All right, so what we did is we built a system on a smartwatch called IOHT, and it's kind of a verbal medication and exercise reminder system. But okay, so there are a lot of medication reminder systems and exercise reminder systems. For this, what we worked with was our telemedicine center here. So it's applied in a telemedicine setting. And when a stroke patient comes to the hospital and they be sent home, they're given the smartwatch with this medication and exercise reminder system. And we built this on an Apple Watch, and it has a microphone and speaker, so it's a very kind of a dialogue system. And it has this first panel showing here is that it is medication reminders and then exercise reminders, other physiological parameters like the EKG that's already on the watch. And it has a panel, and if you don't want to hear the voice because of privacy issues, you can see the responses by text. Now, kind of following our theme is that we want each of these things to be much more sophisticated. So instead of just saying, it's time to take your aspirin, then the person could say, well, how many do I take? And why am I taking these? Can you remind me, should I do it before I eat or with food, things like that. So you can get more information about that. And the same with the exercise. The person could ask which exercise, how many repetitions, how do I do it? Should you show me a video again to how it looks and so on. So that's the kind of idea of moving towards kind of more of an intelligence than just a straightforward medication or reminder system. And so with respect to this, I mean, I kind of said most of this already, but we support kind of general verbal questions for medication and exercise. And by the way, lots of people, especially elderly, are taking many different medications. So this is very helpful for them. And then it also allows rescheduling because people can be busy. If it reminds them to do their exercise, the person could say, well, I'm busy right now, in a general language like that. They could say, I'm busy like that right now, please remind me in an hour. And the same with the medication. And so you can have dynamic rescheduling. And we're currently looking at the quality of the exercise. So instead of just measuring that, okay, the person did the exercise, we're also looking at the quality and trying to also assess the pain levels and get feedback from them on the pain levels that they're experiencing with the exercise. When I talk about hand washing, I will talk about quality there as well. And then we also integrating EKG, integrating other general healthcare dialogue support. So we feel like this is kind of moving in the direction we want to be moving in. Let me show a quick demo of a smartwatch that has some exchange with a person. And this was an earlier version called MedRem instead of IOHT. And the first half is about the watch itself, and the second half shows the information that's in the cloud. Unfortunately, that's a little hard to see. So when that comes up, if you just listen to the speaker, I think it'll be better than trying to see exactly what's on the slide.
Welcome to the demo of MedRem. So I'll receive a reminder. It's for checking ECG. So I tap on the reminder.
It's the time to do an ECG. Do you want to try it now?
Yeah, sure. Please tell me details.
Okay, press the crown to go to apps. Tap on the ECG app and follow the instructions.
Okay, so now I follow the instructions. I go to the ECG apps and now I can do the ECG. Received a reminder for a pill.
It's time to take your nightly medications. Take all medications as directed by your physician.
Please tell me details.
Metformin and carvedilol.
Okay, thank you. Can you remind me after 1 minute?
Okay, remind you after 1 minute.
Okay, thank you.
You are welcome.
So this is the website for the doctors and the clinicians to view the patient data. It fetches the data from the cloud server with the data from the patient gets uploaded. So let's find the data for the patient 2000. So here we can see that the patient ID and the number of reminders provided, the number of reminders the patient responded, the response rate, and the interaction between the patient and the system for each of the treatment. So by this, the doctors will be able to see what exercise or what medication or what treatment did the patient exactly follow day by day.
Okay, so that gives you some idea. Of course, there are lots of other options. You can't show them all in a demo, but that gives some idea of what the app looks like. What we did is we then started to think about how to expand to have other services, and the pandemic came along. So we're saying, well, what else can we add that would help with respect to healthcare with the pandemic? And adding more services based on our theme of kind of continuously having a more comprehensive set of healthcare services. So one is we added hand washing detection, and it's also kind of can be used outside of COVID-19, but I'm going to talk about this in more detail. We also kind of have detection of mood, depression, anxiety, and loneliness. We didn't really do loneliness yet, but you can kind of get that from various approaches. But we did try to detect mood, happy, sad, angry, and neutral, and also anxiety. So the three in red here are three topics that I'm going to present in more detail. Again, this follows the same theme that I just showed. So there's a voice-based conversations, and people can ask for pandemic information. They can say, how many deaths occurred in the United States yesterday? How many new inoculations were there? We go to the web and find that information and bring it back and give it to them. And they can, based on whether it's the mood or the hand washing, we can provide different reminders or alerts or advice. The physiological parameters that are on the smartwatch can also be used to help detect symptoms. For example, the speaker could detect coughing, and maybe there's a temperature sensor could detect a fever, and maybe difficulty breathing can be detected by the acoustic sensor as well. We didn't really do those yet, but I think those are all possible. All right, so let me talk about our hand washing solution, and we try to follow the World Health Organization guidelines, and they have a 10-step process for how to wash your hands properly. And we're going to identify whether people are doing that, whether they're washing and whether they're washing high quality. And if not, we're providing feedback to them to what steps they missed and how long they were hand washing and how to improve their situation. And our solution here is based on a hybrid CNN-RNN, which I'll briefly show. And again, it supports these kinds of conversations, telling them, when to hand wash, and we can detect when they come home that you were reminding them at that point, as well as multiple times during the day, and then feeding back different quality information to them. So here's a picture of the World Health Organization guidelines for hand washing. So it goes from 0 is just turning the sink on. So it goes from 1 to 10. So there's these 10 steps, and we're going to try to determine if a person does all those 10 steps, and also what their total time is. It should be at least 20 seconds. We've actually implemented this on an Apple Watch, and the app has got this hand washing and a reminder system, and you can talk to it and say, yeah, okay, I'm going to go ahead and wash my hands. This is a beacon, a motion sensor that can tell whether you leave the house or when you come back. And so when you come back, we can invoke the hand washing. The dialogue system could look something like this. You're told time to wash your hands. Okay, I'll do it. Then after hand washing, it might say something like, you did a good job, but you should rub hands more and wash for a minimum of 20 seconds. In other cases, it might say you missed the step where you interleave your fingers, and please, kind of repeat that step. And so in this case, it was a good job. So thanks for feedback. You're welcome. And so it supports all these different versions of dialogues related to this. As I mentioned, our solution is a hybrid deep neural net. It combines a CNN. This lower layer here is the CNN. It has 3 convolutional layers with these number of filters, 128, 256, and 512 in these 3 layers. And the reason for the CNN is to detect the spatial properties of the hand washing, whether one hand's on top of the other, whether fingers are interleaved, and so on. And then it has an LSTM also, and its purpose is to detect the temporal aspects. And by combining the two, we get very strong performance. If you're interested, this paper here appeared last year in Chase, and I can send it to you, or you can find it and read the full description of the solution. We did an evaluation where we created our own data set because we didn't have data sets that have details on how people do each step and how many steps and how often they do it and how often they miss and so on. So we had 14 participants. Each one did 19 hand washing sessions. They were all allowed to do 3 practice runs first, and then they did these sessions over the next couple of weeks. And we had video for ground truth. And then we compared our system, which was called IOHT here, this red boxes, to 3 other hand washing systems, one called wristwatch, and then these other 2 are variants, were both in the same paper. But these 3 systems also were trying to do quality of hand washing. And so we can see here we're about more or less 10 or more percent, 10, 12% better on detecting the individual steps than these other solutions. Okay. So now I'm going to change the theme to looking at the acoustic sensor and how can we use this to kind of improve health. And as we know, mental health is really a key ingredient for healthcare, and we've worked on doing distance emotion recognition. So we want to figure out happy, sad, angry, and neutral, but we want to do that even when they're not right next to the microphone. So in this case, we have in-situ sensors, and they're in the home, and person walking around and just going about their normal everyday activity, and they are being kind of monitored, and we can use their speech and detect these emotions. We also have a solution for detecting anxiety, and that's also a very prevalent problem. And that's the solution also handles depression, but I'm only going to speak about what's in blue here, the distance emotion solution and the anxiety solution. Obviously, the acoustics also supports the interactions with the healthcare services. We would like people to talk to the watch, talk to when they say go out in the city and there's a kiosk or something, or some kind of cognitive assistant for healthcare in different environments. They can just talk to it and it'll talk back. So acoustics is, I think, a critical technology needed. All right, so let's look at the first one. So in distance emotion recognition, what we mean is how do we find out what people's emotions are? And let's look at happy, sad, angry, and neutral. Versus previous work, lots and lots of work have looked at, say, when someone like this person speaking is right next to the microphone, or even if they're a fixed distance from a microphone, like sitting around a table. So a lot of work has been done in that area, and solutions have been published quite a bit. And the kind of features needed are kind of almost standard as to what they're used for. However, they don't really work when you get into distance. And so what we're looking for is more of a case where, let's say we have an indoor emotion recognition system and we want to put a microphone in this room, say it's on a table or could be basically anywhere. And then, somebody might be speaking and they're a fair amount away from the microphone or even further, or it could be that there's 2 people or more people talking at the same time, or we have to distinguish between those people, or all of these at the same time, and there's a single microphone in there. And so in order to detect emotion from the person, you have to do speaker identification, first of all, and then you have to also handle reverberation, ambient noise, de-amplification of speech, and overlapping of speech. And so that's kind of the problem we were addressing. And our solution has three parts to it. The first is we want to determine which features are what we'll call agnostic to distance. So what are the good features to use to detect emotion when distance is a problem? And we're going to then take those features and create code words, which I'll explain. And once we have that, we want to do some feature modeling to to represent those code words. And we do that with a new vector embedding called emo2vec, which I'll also explain. And then we put those vectors, these vectors go into a standard LSTM. So this part's not new, but we're inputting these vectors as the inputs to the LSTM. All right, so let's start here on this table on your left. It uses 231 low-level descriptors as features, and these 231 have come from all these previous studies that people have done when they're near the microphone. And the table shows what some of them are, like some of the MFCCs and pitch and harmonics and things like that. And there's actually 77 features here if you add those up. But then you also use the delta and delta of these, and then you get 231 features. So we did experiments where we had microphones at different distances from a speaker. So the speaker would be in one place and talk, and there was a microphone right next to them, one at 1 meter, 2 meters, 3 meters, up to 6 meters. And we found that there was 48 low-level descriptors out of these 231 that are fairly agnostic to distance. And what I mean by that is that the differences in the quality of that metric or that feature doesn't vary by more than 30 or 40% between next to the microphone and 6 meters. So they still vary, but they're not as bad. Some of the other features vary by 100, 200%. Okay, so once we have these 48 low-level features, we decided on that these are the ones we want to use because they're not affected so much by the distance. Then we want to create code words. And let me explain what we're doing here. And so here is, for example, a voice sample that person is speaking, and we're processing that voice sample, and we have like 25 millisecond slices. So in this 25 millisecond slice, we want to extract the features, right? Now we are extracting 48 features, but I can't draw a 48 dimensional space here. So I'll just assume for this explanation that I have just 2 features, X and Y, okay? And so I'm extracting 2 features from each of these slices. And then we can plot them, and we create collections of words like this. So, maybe this first one here is this 25 millisecond slice is this value of X and Y in that slice. And then maybe the second slice is this bullet, and so on. Okay, so then what we need to do is choose how many clusters we want. It's kind of like k-means clustering, and this is a hyperparameter. And then in this example, we have 6 clusters. We say we choose C as 6, we end up with these 6, and we do the centroid of each, and those become what's called these audio words. So now we have 6 audio words. Of course, we're going to use way more than that in reality, but it's harder to keep drawing these if it's too big. So we have 6 words, and now if there's a new point, like now we're testing or we're using it for real, and we have a new point, it's not necessarily that exact word, right? So it could be somewhere in his space, and let's say the feature X and Y turn out to be here, and so we map it to the closest code word, and we use this code word as a representation of that feature. And another word may be also close, and so even though those 2 features were different, they get mapped to the same code word. Reduces the dimension of the space. And we tested basically, kind of 500 to 250 code words, and in increments of 500. And I won't show this here now, but one of the results was that it turns out that different code big sizes work better for different emotions. So for happy, for sad, and angry, we had to use different code big sizes. If you use just one, say average one, then it's not as good as targeting the particular emotion. Now, the next part is that we take these code words and we want to do a vector embedding of them. And those of you are familiar with something like word2vec here. So what people do in natural language processing, if they're using some document and they find a word, then that word is, you could think of it as an audio word, and then, but it's not important by itself. It's what's more important is its context and how it relates to other words. And they kind of create a vector that represents those relationships. And so we're doing the same thing, except for it's not text, it's based on emotions. All right, so let me try to explain this, how this works. So here in this column here that the cursor is showing is, let's say all of these are examples of happy when we're training. All right, so, and code word is the first letter here is the code word. So let's say I have a whole bunch of examples of code word A. And in the training set, in code word A, let's say these are the other code words that surround it, P, Q, R, S, T, and so on. And what we want to do is create a vector for A that represents, kind of this represents happy, but we want to have the relationship to these other code words. And we see that B here is a different code word, but it also has P, Q, R, S, T, P, Q, R, S, T. So it has a very similar relationship to other code words. So A and B should be represented by vectors that are very similar to each other because they both represent happy. Okay, and this is very similar to what happens in word2vec. However, what's different is we also find that, let's say here is the negative examples in the training, and we have a corpus that says it's not happy. So these are all representing not happy. And there's a code word C, and it actually has the same context, P, Q, R, S, T, and so on. So in word2vec, it would assign C a vector that's similar to A and B, but that would be wrong because C is not happy. And so by not only looking at the context, but also mapping it to the emotion, we're able to say C should get a vector representation very different than A and B, so that it distinguishes between happy and non-happy. Okay, so that's kind of what we're doing. So this text just explains what I said, that A and B are, since they're in the same context and for the same emotion, they get vector embeddings that are more and more similar. And then words A and C, even though they're in the same context, will not get vectors similar to each other. Same with B and C. Okay. And then we put this all together. We have up here some some audio stream of a person talking, breaking it down into these windows where we're extracting the features. We're using these low-level descriptives, these 48 that are agnostic to distance. And then for each of those, we get its vector embedding, and then we're inputting that vector embedding into the LSTM. And then the next slice goes into the next step of the LSTM and so on. All right. So that's the overall picture. Our evaluation, we tried 2 literature data sets, and we even created our own family discussion experiments. We had 12 families and 28 people in those 12 families having spontaneous discussions. This was actually done for a project we had with people in Los Angeles. And we ended up having very similar results, whether that we use the literature data sets or our own. Part of the evaluation, we compared to 4 baselines, 4 best baselines in detecting emotions. And we basically were doing 16% better than the best one. And again, here's a paper that if you're interested, it was in UBComp, and if you're interested, you get a lot more details. But rather than showing, this is relative, like we're relatively better than the best baseline by quite a bit. But here's the absolute. And so, for example, I show angry, happy, and sad. And for each, I have accuracy is the blue and recall is the orange. You can see we're really, even for angry, happy, and sad, we're in like the 92% range of detecting these emotions accurately, even at distance. So that was we're pretty happy with that result. We also had this observation that in a lot of the previous work, it was very difficult to separate happy versus angry. And when you use all of those 231 features, many of them relate to energy. And happy and angry both have a lot of energy. So that's, I think, why it was difficult to separate happy from angry. But in real settings, we find that, you know, laughter helps discriminate. And laughter isn't in the data sets that people use for doing these original kinds of evaluations. We also show that what if we used all 231 features instead of the 48? And so if we get rid of features that are not agnostic, what benefit do we get? And so here we show accuracy and recall, and for angry, happy, and sad, and we can see there's about 9 or 10% improvement by getting rid of features that are cause more trouble than they're worth, basically. Also, the kind of final point on this is, you know, we also measured as we move away from the microphone, what happens to our accuracy. And so we do lose some accuracy as we move away, and we find from next to the mic to 6 meters away, we're losing about 5%. But the state-of-the-art other solutions, we're losing about 12% accuracy. All right, so the next topic and final one for today is to look at mental disorder and anxiety. And it's different than mood. And it turns out, you know, 11% of Americans suffer from anxiety. The work we did here is social anxiety. And so there's many different kinds of anxiety, just like different types of stress and so on. But we studied social anxiety. And in previous work, people use fully supervised learning. And it's really, really difficult to label when you use fully supervised learning. And so it's hard to tell which parts of a person's speech are actually representing anxiety. And so this causes some problems and issues. And this is kind of what we get around in our solution. Let me preface the description of what we did by kind of a high level description of some of our contributions. So we basically use multiple instance learning. And that's a weakly supervised learning technique. So it solves the problem of not having to do this very difficult task of labeling very small parts of speech. And then, just like in the previous work, we had a novel feature modeling called emo2vec. Here we have one we call NN2vec. So it follows the same pattern, but it's a different vector embedding. And then we have a new classifier, which is a bi-directional LSTM / multiple instance learning. Previous work has had multiple instance learning with SVM or multiple instance learning with neural net. But as far as we know, this was the first one for applying the two together of LSTMs and MIL. And overall, we get about a 90% accuracy and F1 scores. And we show we're about 17% better than baselines that we compared against. Okay, so what's the problem? Here, let's say we have a person who, this is their speech sample over a period of time. This could be several minutes or something maybe, or even 10 seconds to several minutes, doesn't matter. And let's say within this segment, people can label this whole segment. They can say, this person is anxious. And we don't have to label any piece. So for example, does this part of the segment say there's anxiety? Maybe. Does this part? Maybe. Does this part? Maybe. Maybe all three, right? But it's really hard to pinpoint which parts are really indicating anxiety, right? And this is in multiple instance learning, this is called a bag. So all you have to do is have this segment and label the whole bag instead of the pieces. And a negative one being labeled means that over this speech segment, the person has not exhibited anxiety. And so, again, it's a kind of a high level labeling. Furthermore, let's imagine at this top level here that this is actually the only part of this signal where it really does indicate anxiety, and those other ones really that I circled earlier really didn't. And so if you took this and trained a classifier and said this is a true positive, and I trained a classifier, all this part of the training is false, and it really messes up your classifier because these are not really demonstrating anxiety, and only this part is. And so one needs to be able to understand that and figure out ways of dealing with this problem. All right, so let me explain that in a little bit more detail, and even related somewhat to what we just did on the previous when we were looking at mood. So let's take the same example here with the person's speech, and this portion is, say, a true positive. But we don't know that, right, at first, and we're training, so we're segmenting this thing from the beginning with these overlapping segments. And as we show here, when we basically are looking at the features in this area for this slice of time, and then we're creating a code word from that. And then once we have the code word, we want to understand the relationship of the code word to other code words. And we're doing that with this vector embedding. And we're learning this vector embedding by a standard deep neural net. So let's look at this part of the picture on the next slide, a little bit more detail. So let's say in the positive example that there's a portion here, like it has code words 2, 1, 2, 3, 1, and so on. And this other positive example, which we're training with, has code words 4, 2, 1, 1, and so on. And through the feature embedding, it looks like, whenever there's a 1 here, there's also 2s. Whenever there's a 1, we see a 2. There's a 1, we see a 2. So code words 1 and 2 should have similar vectors. And through the training, the vectors representing those code words are being pushed closer and closer together, right? So that's kind of the feature modeling. It's very similar to what we did in the other work. And then we are going to use this in a classifier. And as I mentioned earlier, prior work does use the SVM and multiple instance learning, or DNN and multiple instance learning. But if you apply it to this problem, it doesn't really account very well for the temporal dynamics in the speech. And so I think that's kind of why they're not being very effective. And okay, here's a really busy diagram. But it's the overall solution. And in this case, let's start over here where I have my audio signal. And let's say the audio signal starts here, and a person is speaking for a while. And as they're speaking, we're again breaking up this into small slices. Each of these becomes a code word. Then after we get a set of code words, we put that into a bag. All right, so this is the first bag. And then we have more code words, we put it into a bag, and so on. So we can take all of these signals in the training of this classifier, and we're creating all these bags, and then people can label the bags. They only have to indicate, for example, in all of these different parts of the speech here, was this anxious or not? Okay, then using these bags of both positive and negative representations of anxiety, we train this bi-directional LSTM, and then the output of that is, when you're using it for real, is a score that says, whether a particular bag is anxious or not. And so if a person's speaking for a while and all of the bags are saying no, 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 then the person's not anxious. If some of them indicating yes, they're anxious, then we're detecting anxiety. Here with the evaluation, I'm not going to talk about the depression, but the paper down here that is referenced, if you're interested, you can look at that paper, and it describes both social anxiety and depression. And for anxiety, again, this is social anxiety, so it was done with respect to college-age students. You can see the mean age is around 19 years old. And it was about doing, kind of public speaking and so on. And so we collect this data from 105 participants, and we get kind of, I'll show you samples of some of the results. So for example, the first thing is, how long should the speech be for us to be accurate in detecting anxiety? And you can see from this graph, so the length of the speech that we're processing is in the x-axis and the F1 scores and the y-axis. And if we just use 1 second, we only get about 83% F1 score. But if we use between 13, 14, 15 seconds, we get 90%. Now, what's interesting, I think, about this is, first of all, it's showing that you do need a fair amount of speech before you can be accurate. And secondly, in a lot of the literature, people use around 5 seconds, which I show here. And so detecting, say, mood, people use about 5 seconds. And even when we were detecting mood at distance, 5 seconds seemed to be, if I drew this kind of curve for mood, I would get the best results with 5 seconds. But for anxiety, it seems like we need significantly more. We also looked at the different audio states. So how many audio states do we want, or code words? And it turns out, like if you have about 3,500, you get kind of the peak score. So also we compared, say, our NN2 vector, which is on this row here, and it shows the F1 score and accuracy in the 90% range. And we compared, what if we didn't use our new vector, but we used the AMO2 vector? Or what if we use I-vector, which is a very popular one from the literature that was developed mainly for speaker identification, but people use it in different contexts. Or we just use the audio words, or we just use raw features. This would be using the original, say, 212 features. So if you just use the raw features, it's really bad. If you just use the audio words that don't represent how they relate to each other, it's really bad. And but if you use our vector, it gives basically about 15% improvement over the I vector. And then finally, I would also say compared, what if we look at weakly supervised solutions, which are these top 3, and we looked at supervised solutions, which are the bottom 4, right? And so, the bottom 4, I mean, you do get, with LSTM, you do get about 87% or so F1 score, but it's difficult to label, and it's not very, it's put a lot of effort into that part of it. And so here we're showing that we're doing about 3.5% better than the best supervised solution. Okay, so let me finish there so we have some time for questions. And basically, I'm trying to emphasize that smart and connected health is going to be based both on wearables and in-situ systems, both in the home and in the external world. And the goal is to push these systems to more ambient intelligence instead of independent apps. And underlying that ambient intelligence is some form of cognitive assistant between the devices and the human. And I do believe that one key modality is going to be acoustics and speech. And let me just finish by thanking 3 of my students, Abu Mandal, Sarat Samyun, and Asad Salakan, who did most of the work that I presented today. Okay, so let me stop there and see if there are questions.
Okay, thank you. Yeah, I have plenty, but I will step back and see if there are others who have some pressing questions for Jack. Great presentation, by the way, and great research. I haven't been following that side of things, but now I know more. Okay, I don't know how we do, Rango, how we do. people can post the question on the chat, I think is the best, and Magda can kind of
Dylan raises his hand.
Hey, sorry, I don't know if this works, but the hand raising usually works pretty well. So
yeah, that works too. Yeah, just Dylan, that.
Or you can just shout out. But
just jump in, yeah.
Dylan, do you have a question?
Yeah. Thank you so much for that great talk. It was really interesting to see all the different methods you use. So I'm actually doing a talk right after you, focus more on movement, and it was really amazing to see, you know, all of the methodology that translates so well, I think, to movement. So a lot of the things that we do follow very similar type of analyses, which again is really interesting. So just one question as it relates to sort of mood and anxiety. All the stuff that you talked about relates to sort of the acoustic environment, but do you integrate movement into that at all? You know, if somebody's not really talking that much, but if they're moving around their space, is there a thought of combining those two?
Yeah, great question. We haven't been doing that, and we've thought about it, and especially, like, for example, loneliness. You know, there are some indicators of how do you measure loneliness, and it could be lack of talking, you know, lack of movement, and so on. So yes, it's a good direction, I believe, but we have not really investigated it.
Okay, thanks. Yeah, it's I mean, the whole body language thing is interesting, but yeah, it opens up a whole nother can of worms, I would expect, than the stuff that you guys have been doing. So thanks.
Yeah. Okay.
I'll just jump in. I have two questions. One is more of a technical question. So you did mention earlier about explainable models, although in your subsequent talk you did not cover that aspect. I'm just curious, like with the audio words and the embedding that you have, like the clustering, whether there's anything that you can like you can connect that or even a subsequent machine learning model to something that's physiologically understandable.
Yeah, so when I was mentioning explainable, what we've done so far is more along the lines of, you know, when people are asked to do something, like if somebody is asked to do a exercise, or they're asked to take a pill, or you know, various kinds of other suggestions are made, they can say why. You know, why are you telling me that I should be doing this exercise? And so there's part of the explanation. Now, I know that a lot of interpretable AI and all of that deals with, you know, can you explain the model itself? You know, like, why did the model come up with this answer, right? And so one of my students was looking into that, but we really have not pushed that very, very hard so far.
I see. Another question, if I'm not mistaken, you have been working in like the smart house field for more than a decade. I still remember we went to a conference together in Jeju Island. So I'm curious, like, in what ways that you are thinking your problem formulation and your approach and translation from engineering solutions to impact real world practices have evolved over time on this topic.
Yeah, that one needs a lot of reflection, maybe, but I think certainly even from the beginning we were trying to always be informed by real world problems and real patients, and I think that's critical. So I don't think that's changed that much. Although I do feel one thing that has changed is that the medical community is more willing to work with us, yeah, and more willing to engage in that, seeing that the potential outcomes are very useful for them. And so I think that's one change. In terms of technology, because of the all of these new CNNs and DNNs and LSTMs, and none of that was really very much in vogue at the time. So I think solutions were much simpler and or relied more on classical signal processing than data-driven models that we find today. And I think there's certain machine learning directions which should apply here as well. For example, dealing with uncertainty. There's been a lot of work in AI and machine learning that people are worrying about how do you deal with the uncertainty in the models and what they predict. And I think that's even more important for smart health than for a lot of other applications.
I see. Well, what about the gap between technology and practice? Do you see that we are closing it?
Yes, I mean, I think there's lots of things where technology that has been developed is being used. And both in terms of, kind of experimental studies, but also even in practice.
I see. Yeah, thanks.
Anyone else? Okay, I'll chip in. Jack, one follow-up with Ron's. Now, you said your system smartwatch in this particular case gave recommendations, etc., etc. Did you observe any resistance or any aggregation from the patients that why you are asking me to do this? I don't care. I know when to do this or that type of thing. I remember my mom, rest in peace, used to be aggressive in these manners. So did you observe anything, and do you have any solutions in that regard?
Yeah, I mean, actually, I can tie this back to Ron's question to some degree. Like I'd say 10 years ago, there was a lot more resistance, but there's still resistance. So, for example, in putting microphones on in people's homes, there's still resistance. Some people will not allow us to do it. So when we look for real patients or real deployments, I'd say probably 30 or 40% of the people end up saying no because they feel it's too privacy invasive.
Yeah, but my question was more on the personal level. For example, if I am wearing this thing and I am constantly getting these warnings, I might get aggravated and frustrated type of thing. Did you observe these type of behaviors from the individuals themselves?
Not really. Partly because we try to minimize the interactions.
Okay.
So for example, one study we did, which I didn't present today, was on family eating dynamics for overweight families, and we have queries and interact. They're supposed to be wearing their smart watches, and then if we detect eating, we ask them some questions, how hungry do they feel, things like this. But we limit the number of times, so the system will not ask questions more than once every couple hours.
Okay.
And so we try to mitigate that problem, and we didn't find, at least I don't recall finding any pushback on people saying we bother them too much.
Okay.
Maybe it's partly because they're willing to do the study in the first place. That it's kind of a chicken and egg problem where they're excited by the study, they want to be involved with it, and so they don't think it's so much of a burden. But if you put it, you try to give it to people who don't want to do it, then they won't do it. They won't answer, they won't use the system.
But at some stage, particularly dementia patients would become less cognitive, so their behavior or their acceptance may vary even over the day, within an hour. So
right. So in our case, though, we're focused on the caregiver, not the patient.
I see. Okay.
So we're interacting with the caregiver, and the idea is that if they don't find it's effective for them to reduce their stress and so on, then they'll stop using it.
Okay.
And that project is really early, so I don't have a good answer for how many people will give up on it.
Okay, I have one more question, and I think we are already out of time. Now, when you build up your code words, are they really real English words, or can they be gibberish?
Yeah, they have nothing to do with English words. They're gibberish. They're basically, you know, kind of representations of the features that are in the signal. So yes, they're called code words because they're not English. They have nothing to do with English words.
Okay.
Yeah.
Okay. Thanks again for the great talk. Any other questions from the audience or from the others?
Actually, I do have a question. So if a person is already struggling with dementia and is having a hard time remembering things, you know, family members or, you know, how to do things, having a technology that it's so, you know, not what they remember, isn't that scary to people? That, you know, this is something out of this world. They've never, you know, whatever memories they have, it's probably not to do with, you know, technology like that. And I'm thinking it's a huge thing, you know, waking up one morning and having this watch talking to you.
Yeah. Well, I mean, I completely agree with you, and especially for late stage. So, you know, dementia doesn't happen just overnight, and there's early stage, there's mid stage, there's late stage. And so we're concentrating more on early stage as well as with the caregiver. And so, you know, there are a lot of projects and people worrying about the patient and, you know, how to improve the patient's life and things like that. And so once you get to late stage, yes, I don't know, we're not working on it, but it's a good question. And I don't think, you know, technology is going to help very much at that point.
Can I just have a quick question? Like, because as I already mentioned, that as my create is a training program, we have a lot of students in the audience. I wonder if you can share or give some advice on how to undertake this type of research, which is actually interdisciplinary, like especially for someone who's maybe coming from a purely engineering background.
Well, you know, I think we're all my students and myself, we come from an engineering background. And one thing that really helps is that at UVA, we have something that we started, which is kind of called embedding. So students from engineering actually embed with the hospital or embed with the doctors or clinicians for like a day a week, or they go and they really see what's going on. It's eye-opening for the students where, you know, they realize that sometimes their solutions are way too simplistic, or for example, students will still on a smart watch, they will draw things that nobody can see unless you're, you know, kind of a 20-year-old who has perfect vision. And, you know, it's supposed to be used by elderly. It just makes no sense. And, or, you know, that they train where we have perfect English speakers without mumbling, you know, and a lot of elderly who are, you know, not feeling well are going to mumble, or, you know, that they don't always have crisp English phrases and everything else. So I think engaging with the medical side, the healthcare side, as often as possible, and even seeing real use of what they do will inform how you develop your own solutions, technical solutions. And
that's a great tip. Yeah.
And that actually reminds me, answering your earlier question, 10 years ago, we would have to develop stuff and give it to them and then have them react. And then say, you know, no, that's not what we want. That will never work on a real patient. Like, and we wasted all our time. And now I feel like they are engaged with us from the beginning, and we can work more collaboratively in identifying the real requirements and getting inputs early on to avoid these false starts.
Yeah, that's a very good point. In fact, in our program, we also have the element of observership. but we cannot, start it because of the pandemic.
Yeah. Well, good
Okay,
luck on
so-
your program. I think it's a very exciting program.
Thanks.
Okay, I think we are done with this, and I'm just checking 2 minutes into the next. So I would like to thank Jack again for the presentation and advice, and hope to engage you, Jack, in our future endeavors. Probably your skills and your background and your expertise will help you to refine certain things that we will be doing. Thanks again.
Okay, you're very welcome. It was my pleasure.